Okay, hello everyone. So I'm not sure if there are other people listening there. So just as a reminder, you may want to go on the on. Okay, hello everyone. Wow. So I'm not sure if there. So we're gonna have a huge echo. So I've just got my the sound. So if you go on the GitHub webpage of the webinar, you'll find various links. The first one is a link to the YouTube screencast that you should be able to follow now. And you should see the slides of EVO, the Popper Experimentation Protocol. Don't forget to use the pad if you want to put any questions. There are like 5 or 6 people around for the moment. Just put the question there, and then EVO will process them as you see them. Okay, let's go back here. I'm going to cut my microphone.
Okay, so should I start now? Okay. Thank you very much for this opportunity to talk to you about Popper, the protocol, the experimentation protocol that we've developed at UC Santa Cruz, collaboration with folks at University of Wisconsin-Madison, Lawrence Livermore National Lab, Sandia National Lab, and the University of Utah. Today I'm gonna introduce first the experimentation protocol, and we're gonna at the end hopefully work on a hands-on exercise. So just to motivate the problem, and for the sake of completeness, I guess we've all been in this situation where we're reading through an article, and when we get to experimentation section of an article, the experimental evaluation, sometimes we come up with questions that might be hard to answer just by looking at the text, and simple things like how was the binary, how were the binaries compiled, which flags were used, how was a subsystem configured, how does the workload look like, which properties a particular workload has, and so on and so forth. Questions that are hard to answer by just looking at the text. And if we reflect on this situation, on this scenario, and we contrast with what other people do in other domains of empirical sciences, we kind of can see that we would benefit if we had something like a lab notebook, which other domains of science use heavily and rely heavily for the experimentation. And this is basically just a record of what was done and why throughout the life of an experiment. And if you've used version control systems before, we could kind of make use of a version control system and use the commit log as a lab notebook, because a version control system is, again, it's also a record of what changed, and if we use commit messages and we describe the changes we've done, we know we have a record of why was a change done and what was changed over time. The problem is that just by putting all of our experiment assays on version control doesn't make it repeatable automatically. So in our work, what we do is we try to systematically go through how would we organize the contents of a repository so that it makes it easier for others to re-execute an experiment. And to work on this, we try to abstract any type of experiment, and we came up with this very high level workflow of how we in general, or we think at least 80% of experiments would I mean, following the 80-20 rule, there's a big chunk of experiments that can be abstracted by this diagram. And we a lot of us first code our experiments, and then we package that code somehow, and we might be generating binaries and distributing those binaries manually or through software packages like Linux packages, or through some other means like virtual machines or Docker containers. But we eventually deploy that code in the machines where we want to run our code. Then we execute that code by uh, and maybe use input data, generate output data, analyze those results, visualize those results, and then at that point we might want to go back depending on what we're finding. We might need to go back to the code and add more features or fix a bug, or we might want to try with another input data set, or just tweak a bit the parameters of an execution, and analyze and visualize again. And optionally, at the end, uh, we might want to report results in the form of a manuscript, either like a tech report or an article or a workshop paper or something like that. And if we look at this diagram and we contrast it with what people do in software development communities currently, um, we see almost a one-to-one correspondence. And in general, it's not just software development, but a more broader term, which is DevOps. And I'm sure maybe you've heard this phrase um, in other in it's a very popular term, but it refers to the merge of two communities, which is the development community, the software development community, and the operations community. And their practice is the goal of their practice is to reduce the time that it takes to incorporate new changes to a software code base and deploy those, test that code, and have that code running in production as fast as possible. Basically, have a fast iteration loop of changing code, building code, testing code, deploying it, and making it taking it to production, and get feedback as soon as possible. And if we reflect on the previous diagram that I show you on how that compares to what people do currently, we see this one-to-one correspondence because we're managing code, and these people doing software projects manage code. They also have input data in the form of test examples, and they analyze results by looking at the results of those tests. They validate their claims by doing many things like continuous integration and regression testing. And they also write about results in the form of documentation or bug reports and things like that. So the key idea behind the Popper protocol is, if these people working in these software development projects, in particular in the open source software world, are doing this already, why don't we manage why don't we manage a scientific exploration like these people manage software projects? And that's the main idea behind Popper. If we look at this very broad, very big ecosystem of what people do, what people use. We find a bunch of very useful tools. The it's called the or people refer to this as the DevOps toolkit. I'm just showing a small sample of of tools, but basically for at each stage of this very high level workflow, we find a lot of tooling available, very mature tools, open source tools in their almost in their entirety, that are the tools that are well documented, that are used, that have big communities around them. And the goal and the idea behind Popper is just make use of those, create scripts at each of these stages for those tools, and grab all that in a version control system and record as changes as we go in the form of commits, and just use this as the basis of collaboration for managing scientific explorations. That's in a nutshell what the Popper protocol is. And uh, just to be more concrete and to give you an example of what the DevOps practice looks like, uh, think about what we usually do when we're carrying out a scientific exploration. We usually work on live, what I like to call quote unquote live systems, which is just logging into a shell to terminal, logging into a system, and start to try to carry out our exploration. We usually use a lot of trial and error. It's a trial and error loop where we try something, doesn't work, and we try it again, and then we keep going up to the point where at the end we arrive to our our result. The problem with that approach is that by the time we're done, it's really hard to reconstruct what we've done, because we don't have a clear record of what worked and what not worked, what didn't work. So in the DevOps world, what we do instead is we write scripts, and we give those scripts to automation tools so that these tools do the work for us, and we're just basically just providing a list of steps that these tools should carry out. And the nice thing of this is that by the end, when we get to the point where something worked, we have in the script the list of steps that were carried out in order to get to our result. So this is in a nutshell what DevOps, at least to me, it's a very practical way of defining DevOps. It's basically, instead of manually typing things and doing these on live systems, DevOps is basically a bit more systematic in the way that, in the sense that you first write what you want to do in a script, and then you provide this script to other tools, automation tools, to do the work for you. And all of the systems that I show you here work on this way, and allow you to, the nice thing of scripts is that you can put scripts in version control and then keep track of those changes in the form of commits and commits messages. So if we do this, if we follow this 3 steps that I mentioned, and just to recap, number 1, we pick one or more tools at each stage of this experimentation workflow, and we then uh, put all these scripts in version control and document changes as we go. If we do this, then at the end we have what we call popper compliant experiments, which is basically an experiment that is self-contained, that for which we have everything we need in this version control system. So we can actually, for example, clone a repository that is on GitHub, and by cloning it, we have everything that that person, that the original the original person that implemented that code did. We have everything there, either in the form of just the code, the scripts there, or references to other datasets that are not part of the project, the repository. And just as part of this effort, we have a command line tool. So, and at the end of the talk, we will go through a hands-on exercise. But just to give you an idea of how this looks like, this works with a Git repository. So you have a Git repository that you can initialize, and you can browse through a list of already what we call popperized experiments, and you can import these experiments into your project and use these as a baseline for your work. And these experiments, or the projects, they look like something like this. It's a common a convention for structuring these experiments. We have an experiments folder, and every subfolder has an experiment in it, and we have an optional paper subfolder that would have the manuscript. And inside every experiment folder, we have this scripts, and we will talk about this and why they are named like this. But in general, you have scripts, and depending on the tools you're using, these scripts are going to be different. But in general, this is the common structure. And by having a convention on the structure of the file system contents, we can actually automate the execution of these experiments, which is what I'm going to talk about. This, how do we complement this experimentation protocol with continuous integration systems? But I want to pause here and see if you guys have any questions so far. Okay, so all right, so I'm gonna keep going then. Just give me 1 second. All right, so I'm going to talk about how we integrate this our experimentation protocol with continuous integration systems. If you haven't heard of continuous integration systems or continuous integration in general, this is a very high level description of what it is. So basically, in software engineering and in DevOps in general, continuous integration is the practice of continuously merging changes to a main line of a code base. And what this looks like is you have multiple developers pushing changes to a version control system, a server, and then the continuous integration system is basically just pulling those changes and merging them, testing them, and checking whether that merge to the main line is causing any issues. And if you do this as soon as possible, then you try to avoid uh, any potential conflicts. And that's basically what people do in practice. You might have heard of Jenkins or Travis and Circle CI and all of this continuous integration systems that have a cloud type of offering. And in our case, we 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 use a CI system to continuously validate scientific explorations, and we're able to do this because we have this common structure for a project that I mentioned, that I briefly mentioned earlier. And the goal is to automate the end-to-end execution of an experiment. Um, so we have a bash-oriented interface, which is these scripts that I show you that that I'm showing you again here. So basically, as part of our the command line tool, we also have this scaffolding feature where you can initialize an experiment, and it will the CLI uh, will create these scripts for you: a run bash script, a setup bash script, and a teardown bash script. And they're initially empty, but you have to put things on those inside those bash files, so that you specify what it's executed. Just to give you an example, for example, as part of setup, like in our case, we do a lot of distributed systems research. So we actually have to deploy and configure infrastructure. So the setup phase, we might be, for example, initializing resources on the cloud, on Google or Amazon, or internally in our institution. And as part of the execution phase, we might maybe use a job scheduler or other type of resource manager interface like Kubernetes or Slurm, or in HPC world like a batch scheduler, or just run directly. It's up to the experiment and what you're using. And then at the end, we tear down. We basically just release all our resources. And this is another example of what we do. Here in the US, we have Cloud Lab, which is a government-funded bare metal as a service platform that researchers can make use of. It's basically similar to Grid 5K. And in this case, the setup phase from one of our experiments is making use of this Jenny tool. This Jenny tool allows you to specify in a Python script. It's a very nice way of, very concise way, very succinct way of specifying the resources that you need, how the network topology looks like, how are you going to deploy those bare metal machines. And in this case, we just boot a bunch of Linux boxes running Docker, and then using Ansible, when we run, Ansible, you can think, if you haven't heard of Ansible, it's basically, conceptually, it's kind of like a distributed SSH tool that allows you um, to implement a bunch of tasks in a cluster using just SSH and Python. And with Ansible, once we boot the resources, we pull Docker containers, we run them, and then we fetch results. And then at the end, we we can report whether the experiment failed or whether it ran to completion. Um, and also, as part of the CLI, we have this check, proper check command that for which you can check an experiment, and it will go and run each stage, and at the end it will report the results and the status, basically, of whether you run or not. And this works, basically what I've been talking about so far is automating execution of an experiment. And the 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 other thing that we also work with is actually the output of an experiment, looking at whether we can validate the output of an experiment. And in order to do that, we use what we call codified validations. And a codified validation is it's basically a way of expressing uh, our expectations on the results. In this case, we use but in our work we do a lot of performance metrics gathering at runtime, um, and you can basically think about this as having a record, like a log or a CSV file. In this particular case, we have a CSV file that has a bunch of performance metrics, like the number of nodes that we run our system on, the throughput, the row bandwidth, and a column that denotes whether the network is saturated or not. And we as part of our work, we developed this very tiny language. It's basically just like an if then condition evaluator. And with this, what you can express is things like this statement right here, which is saying, okay, so for this experiment, I expect to have a linear relationship between the number of nodes in my system and the throughput. So basically, I'm checking for linear scalability of my system. If I'm, for example, working on a storage system, I wanna validate that as I add more nodes into my system, the performance of the system scales linearly. And we can also express other type of things, like when, as long as the network is not saturated, the throughput of my system should be uh, at least 90% of the row bandwidth available to the experiment. And there are many other things that we can express with this, and we doesn't necessarily need to use our language. We can check a bunch of things using Jupyter, I mean Python or R, using in general any uh, analytics framework that allows you to take the output of an experiment and just check any conditions you might want to be checking. Basically, we're codifying the claims that are made in a paper. And if you contrast this with what the state of the practice is usually what we have nowadays is that people write just observations on a graph. For example, we see that the speed up of the system is X, but by doing this, we're actually making it possible for a machine to verify whether we are actually obtaining the results that someone obtained originally. Um, so the this is usually done at the validation phase. I show you the scripts that we have as um, part of the scaffolding features. So, oh, sorry, I didn't have it here. But we have you would usually put this on there's a validate.sh script that you would put these that's the phase where you check this, um, and if we do this, we can actually add a new stage of at the execution of an experiment, which is not just execution but also validation, verifying the claims hold against the results that we just obtained. And if we do this, then we can have one more type of status for an experiment. Because before I show you, we had basically a pass or no pass type of status where we failed or we succeeded. And but with this, we call it gold to the status of not just running or correctly, but also um, but if you also pass all the validations that are executed against the output of an experiment, then you also get a gold status. Um, and this is a pipeline of how we would set up this to run to be able to run on a continuous integration system. You usually what you would do is you would have your project on GitHub, and then you would um, configure one of these systems. And then when you commit a change to your experiment, you trigger an execution, and then you run your experiment. And and depending on which platform you're using, you would go and execute the experiment, then generate results, come back and check and validate the experiments, and then report on the results. Um, and as part of the CLI tool, we have a way of generating configuration files for so far for Travis, and I'm going to show you later how to do this. And our plan is to incorporate more things, other CI systems like Jenkins and Circle CI. And the goal is to make it very easy for people to be able to incorporate their projects and to make use of CI systems in their projects without having to deal a lot with the just the trivial tasks of configuring the pipeline. The nice thing of this pipeline, of the Popper pipeline, is because it's a convention, so we are actually able to simplify a lot of things. So by structuring projects in this convened way, there are many, especially what it's called. It was made popular by the Ruby on Rails community. It's the notion of convention over configuration. By having all these conventions on the structure of the folders and the scripts and the entry points to the experiment, we simplify a lot the configurations that we have to do on these systems. And just to talk about batches, so if you're familiar with batches, this is something that people do in the open source world. If you've seen GitHub, there are these type of batches that are placed in the README file of GitHub projects that denote multiple uh, aspects of a project, uh, like things like whether a build is passing or not, or how the percentage of coverage in your code base and things like that. So for Popper, we have these batches that we serve, and that denote for a particular experiment, the README of an experiment. They denote what's the status of that experiment. So if you push something, you will trigger that execution on the CI system, and if something failed, you would get a fail badge. Um, if it worked, then you would get the green badge, and if you pass the validation, you would get the gold badge. And that's a nice way of kind of like showing other people what's your kind of like your status, instead of reproducing your work. Um, and a bit of of how does this relate to other things that have been recently proposed, in at least in the computer science world. The Association for Computing Machinery, they they just released like 6 months ago the policy on artifact and results batching, and they have this different terms on what does it mean to reproduce, well, repeat, replicate, or reproduce a result. And and in the first case, repeating a result means that an original author um, can get to the same results using the original artifacts. They call that repeatable results. Replicability is a third party, so basically someone else that is not the authors. They take the same artifacts and generate the same results. And reproducibility is basically just re-implementing from scratch everything and getting to the same results. And with if we contrast this with the badging, the ones that I show you, because of a CI system can be seen as a third party, because it's basically executing experiments for you. If you get this gold badge using a CI system and following the Popper convention, you basically kind of like automatically in this category of results replicated. Some conferences and journals are starting to use these batches, uh, and the goal is to have more and more journals and conferences to use this, and make it more common to have authors pay more attention to this, to the repeatability of results and replicability of results. So with this, I get to the end of the talk, and I think if you guys have more time, we can move to the hands-on section. Um, but I would like to check first whether you have any question so far. I'm looking at the path. Let me go over this. Okay, so there's a question on the path, which is when you use a CI system, there the automation server it's going to basically be running things on your behalf. So how do you deal with credentials, um, so that you can, for example, log into to other infrastructure? And the way this is usually deal with is people deal with this in practice by, like, all these systems have a credential store associated to them. So, for example, in Travis, you can set up secrets. In Jenkins, you can do the same. And the way that this is exposed to an experiment is by having environment variables. So you have an environment variable that is, for example, a password, and then you use that in your scripts. You assume that in your script there's going to be for example, an environment variable called my my experiment or something like that. My user or something. So there are environment variables, and for example, um, my user and my password, and then in your script you make use of this, and there are other nice features. For example, Jenkins will obfuscate this in the logs, so when you print those, they are not showing, Jenkins is not showing the content of that variable, it's showing just stars. um, and then the other question is uh, whether we need to implement all the scripts, or can we just have one of them, for example, the run .sh portion. uh, oh, I see. So whether oh, I see. So if you have, I guess this question that I'm looking at right now is whether you can run multiple experiments on a single deployment. um, I guess you can. I mean, it's up to whether, how do you want to organize an experiment. But yeah, I guess, yeah, we hadn't thought about that. Maybe we can have like a global deploy and then go through each experiment separately. Um, uh, yeah, so whether we can run multiple versions of the same experiment, the same resources. Currently we don't support that, but I can see we could deal with that in such a way that you would have like project level deployment or infrastructure configuration, and then you would just do it once for the entire project, and then you would go and execute either multiple experiments or multiple versions of an experiment. um, and yeah, that's something we could work on. um, um, I can, if there's no other question, I can go and show you this, which is how do we connect a Travis account to how do we enable Travis for a project. Um, so when we have a project, when we have a project that we want to have version control for, I mean continuous integration. We want to enable continuous integration for a project. We will have we basically go into a project and we say, oh, let me just start from scratch. So we first create a project, and we initialize it using popper, and we will have a popper YAML file, and then we can add this and just commit this file to the repository. And then when we do this, we can, as I mentioned, we can have we can show the list of experiments that are available to us, and we can either import experiments by doing experiment add. For example, in this case, Bliss, you will see that we will have that experiment imported. We have scripts. Another thing is that you don't have to implement all the list of scripts that I showed. You just have you can just have a run experiment, a run script, and this will allow you to have a green status. You won't get the gold one because you're not validating results, but that's fine for some experiments. Maybe that's enough. And so we can add, commit this, and then if we wanna if we were in GitHub, if we had this experiment on GitHub, we would be able to go to GitHub and for example, see see the experiment here, the project here, and then once we have it on GitHub, we can go to Travis, and in Travis you will create an account, and you here see on to the left you see the list of projects in your repository that you have Travis enabled for. And in this case, I have this already here, but if you didn't have it here, you would click on this plus sign, and this will show you a list of all your projects on GitHub, and you basically just turn this on if you want to enable Travis for some of your projects. And this particular one that I'm enabling, it's actually another popperized experiment for another journal publication with it. But the one that I was showing you was this one. And then once you have this enabled, this is going to be empty. Or let me show you the one that I just enabled. This is going to be empty, and it will tell you that there are no builds for this. And the way you trigger a build is first you add this Travis.yaml file, but and you will need to write it by hand. But because we're popperized and we have everything, we're doing everything by convention, you can just do this popper ci Travis, and this is going to generate a file, this Travis.yaml file, and you can look at its contents if you want. It's basically downloading a Python script that we wrote, that it's basically implementing the popper check command. It's going over each of the stages and checking the experiment. And then once you have this file, you can add it to your project. You you commit it, and then you say, okay, adding Travis configuration. And then if this was connected to GitHub, we would do git push. I haven't created a repo for this yet, but if you had one, you would push this, and that would trigger an execution on Travis, and you would see something like this. And this log would be this would be displayed in real time. So in this case, where Travis is cloning the repo, then because we had Docker enabled, it's starting Docker, installing Python, the version we need for this. It downloads the script and it actually runs this. And here's the popper part where it's checking that the experiment runs. And at the end, we have a success success status because we were able to run it without any issues. And as I mentioned earlier, as part of our popper CLI, the popper CLI tool, we can execute the popper check, which is with the same command that would run in Travis, but we can run it locally first. This is helpful so that you can check first before pushing your changes. You can do popper check, and then that would trigger an execution locally on your machine. And I'm gonna then we have this popper check command has flags to define environment variables, and this is helpful so that you can deal with what was asked before, which is, what if I have an experiment that it's getting an environment injected from the outside in the form of environment variables. So you can say popper check that -e, for example, and define a my user variable or a my password variable, and that's gonna make your scripts those variable available to them. And so, for example, let's say you had a user and a password variable defined so that your script can log into some other system that it's running somewhere else. That this flag allows you to define those variables, and then in Travis you would come here and define for this repository. You would have here you have a way of in the settings you have a way of defining new variables. This is where you define this, and you can say my user and then a value, and whether you want to display these on the build log or not. If you choose not to, it will actually swallow those lines, and it won't show any line that it's using that variable. And this allows you to hide secrets that you might be using for your executions. What else? So I have to I'm going to look at this error that Arnaud just reported regarding that this might be an Ubuntu issue. I'm gonna check that, and then I'll update the path. So there's a question that says there's a skip argument to skip stages, and where are these stages defined? So these are defined. The stages are defined by convention, and we have what these are the stages that I referred to earlier, which is the setup phase, the run phase, the validate phase, and the tear down phase. So, but you might want to say, okay, I have, for example, if you're doing this interactively, you might have executed once and the setup worked. So basically you run popper check and the setup worked, but the execution failed, and you want to rerun again, but you don't want to redeploy or reconfigure hardware. You say, okay, I want to skip the setup phase. You might want to say, okay, I know that the infrastructure was deployed correctly. This is basically just to support more interactive / debugging scenarios where you want to test other things. And regarding codified validations, yeah, this is so basically the convention here is that the script generates lines in the following form. This script is going to print true or false, and then it's followed by a description of the validation that you're checking. So it's something like this. So it's true or false, and then a description of the validation, and then the popper check command is gonna look at the validate output, validate sh output, and it's gonna look at those. And basically, if you have all true output, then that's what you say, okay, this is valid. All these statements were correctly verified. And if there's one, you don't have to have multiple. You might have just one, but you might have more than one. So if you have more than one, if any of those is false, then you're not validating the experiment. Only when all of them are true is when you're validating, when you get a gold status. And I also, it might be like worth pointing out that this validation phase might be very complex. Like in our case, we're dealing with CSV files, small CSV files, but other domains, like for example, we work with numerical weather prediction folks that are using Popper. They actually have very big data sets. And this validation phase it might entail triggering another like big pipeline on a remote server. And because you might have like big data sets and you might have to execute, for example, a Spark server, and you might need to do like a distributed type of statistical analysis on the output. But at the end, what we want, it's basically a Boolean that tells you the experiment generated the same results or not. So is this code a Python library or elsewhere? This can be implemented in anything. This is basically the validate data sh command is it's just the entry point to that phase, to that stage. So there, for example, you might be your validate data sh file might be, for example, invoking Docker, or it might be invoking, as I said, you might be maybe like launching another task in a Kubernetes cluster, and then you wait for that Kubernetes cluster, for that task to finish and report on the results of the validation phase. So the valid data stage, so all these scripts, the run script, the setup script, is just entry points to that stage. What is written in those scripts? It's domain specific, and as I mentioned, for example, in the weather prediction community, what you see in these scripts, it's basically you launch MPI tasks that deal with a data set that you just produced, and they check those outputs. In this case, these are netcdf files, and some of these netcdf files are big, and they are placed in distributed storage. So you're launching, you can launch, for example, a Spark cluster. You deploy a Spark cluster that is used to analyze a netcdf, a very big netcdf file that obtains statistical information about the output, and this boolean is actually it looks like something like a confidence interval, and you say a confidence interval within this range, and that's what you look at. It's not actually looking at exact numerical values. It's a bit more sophisticated. So there's another question that says, what if you realize after looking in more detail at the data that your validation is too simple or should change? Should you rerun the entire experiment in order to kind of corroborate this change, or to implement this change? Yeah, so this is related to what I mentioned earlier. So that's why you would use the skip argument, if assuming you're in this interactive mode of or debugging mode, where you run something and then you validate. So that's what you would use the skip argument for. So you wouldn't need to. You would say skip setup and run, and maybe tear down too, because maybe you don't want to tear down anything. You just want to run the validation phase. Yeah. Cool. Any other question? Awesome. All right. Well, thank you very much. I really appreciate it. I hope I got you interested in Popper. We're building a community around this project, and we're trying to get people interested in this and see what are the use cases that people have in mind and whether Popper fits those use cases. And if not, then we want to address those needs. We're working. We have a lot of plans for working on making it easier, for example, to compare results. Once you execute, you want to check what are the differences we also with previously obtained results, and And we're basically just looking for more people willing to implement their experiments using Popper and getting feedback from those people. So I hope I got you interested in using Popper. And thanks a lot. Thank you.
Ok, well, alors pourquoi ça... Ah oui, non, mais c'est là. Pourquoi c'est pas ça? De quoi? Ah oui, c'est juste rouge noir. Okay, looks like I'm quite tired here. So thanks a lot, Ivo, for explaining all this and explaining the internals, how they work, and everything. Especially that it's 5 a.m. or whatever. It's very early for you. So thanks a lot for all this. So we're gonna have a summer break. So I guess no more webinar like in August. I think September is generally a bit crazy, so I'm not sure we're gonna have one in September. So anyway, I'll keep you posted about new sessions. And so have a nice summer break and vacation for those of you who take some. And thanks again, Ivo, for everything and doing this very nice presentation.
Sure. Thank you. Thanks. Bye-bye.
So see you in October or something like that.
Yeah.
Bye-bye.
See you at the supercomputing if you're going.